Great. Well, thank you for inviting me to come and talk today. I will be talking about sort of boosting energy system resilience in the face of future weather extremes. And this is really a collection of different research topics or student work that's been done with myself, looking at how extreme weather is impacting various different parts of the energy system. And it's sort of hopefully giving you a flavour of the diverse ways in which weather can be kind of maybe problematic, and how we might actually go about using some of the techniques that we use to look at extreme weather events to think about how we might sort of target our interventions to try and help boost resilience in the future. Right, so to start off with, I thought I'd start with some images just to remind us of how weather can impact various different parts of energy infrastructure. So it's starting off with catastrophic failure of a wind turbine, sort of wildfires going through a solar farm, the sort of classic sort of wind and falling of trees on kind of distribution networks, fire risks to the transmission system, and also sort of flooding of substations, and the bottom one's supposed to represent the sort of growth in kind of proliferation of air conditioning use in various countries as sort of energy demand kind of grows. So we can see that, you know, it's quite varied. It's actually kind of impacting all different aspects of the energy system, from generation through kind of distribution and transmission, through to kind of demand aspects. So it is something that we need to pay attention to and think about how we can design our energy system so that it will be best to withstand these sorts of events in the future. So this is my schematic that will be kind of like guiding me through the talk, and I'll be talking about various different bits of work that we've been doing, looking at how extreme weather will impact kind of generation, transmission, distribution, and demand. But before I start with that, let's think about the system as a whole. And this is work that was done by Eleanor McIndoe, who was a MSc student a couple of years ago, and we were looking at the impact of heat waves on the energy system in Australia, in Victoria. And she looked at the causes of 7 really large-scale heat wave outage events, and tried to classify what the different kind of impacts were during those particular events. And you can see that there's a large number of kind of statewide impacts that were impacting on transmission, generation, and distribution, mainly from high temperatures, a few kind of sort of equipment failure issues that arose as well, and some sort of storm damage. But equally as well, there's very much more localized different centers that emerge, where you know, there's obviously large generation kind of activity that's going on in this region here, and that's why it was sort of more impacted by these particular types of event. So during these 7 outputs, 7 large-scale heat waves, there were 12 separate incidences of load shedding, and actually 2 incidences of over a gigawatt. So sort of 18% of the average peak daily summer load. So these were quite significant impactful events just from heat waves. So we tried to dig into these in a little bit more detail to see what the sort of impacts of these particular events were. So and I'm going to categorize these by the number of customers affected by the different kind of causes of outage, the customer minutes lost, and also the frequency of outages. And the thing that you can see from each of these events is the main contributory factors are sort of overload, but also weather is coming up as quite a strong influential factor in causing these disruptions to the system in both of these different cases. There's sort of also different kind of timescales. So there's in the far one, it's sort of like at what time of day were we actually seeing the disruption. So most of the outages were kind of in the early evening time, where there's obviously getting failures, but also kind of weather impacting on the system as itself. So if we get these kind of heat waves kind of concurrently happening, then it will greatly exacerbate the stress on the system and the severity of the outages that we're seeing. So now I want to sort of introduce, I think, which will be a concept called probabilistic extreme event attribution, and this will be the sort of technique that we're using through most of these results that I'll show you to find out how much extreme weather is changing, how much extreme weather is being affected by climate change, and so how much worse these or better these events might happen in the future due to climate change. So the way in which we do this is we use large ensembles of climate model simulations that simulate the world as we see it now, in this case, the kind of green line for an example heat wave, and then we run it with a future kind of climate warming scenario. So, you know, in some future climate state. Typically, when we're thinking about an extreme event, we've got a particular threshold that we're looking at, and then we're comparing the different probabilities of seeing, in this case, a heat wave event that is as severe or worse than this particular event that we're looking at, or is exceeding our threshold. And so we can get a probability ratio to say how much is the likelihood of that event changing with climate change, of seeing those kind of things. You can also think of it in terms of return time or return period, and this will be saying how much how rare is it that we see these particular events, and how these events in this case are becoming more frequent with future climate change. So in this case, what was a sort of a 1 in 50 year event is becoming a sort of a 1 in 5 year event that we're seeing. The other way that you can look at it, which I think is also particularly important for engineers who are designing systems for particular event severities, they might say, I'm designing something to withstand the 1 in 50 year event. Then you can look to see how the magnitude of that event might be changing under future climate change. So the idea is that the threshold that we're designing infrastructure to for a 1 in 50 year event now is not going to be the threshold that we need to build it to for a 1 in 50 year event into the future. So that's another kind of useful piece of information that we might get from this type of analysis. So Now I'll come on to some results, and this is work that was done by Sarah Abdelaziz in her DPhil thesis, where she was looking at UK offshore wind generation and sort of where we can go about siting our wind farms so that they'll be most resilient to changes in extreme weather in the future. The first thing is to think about the operation of a wind turbine and how much power we get under what conditions. So here we've got a sort of power curve, which is from different kind of wind speeds to how much power we're getting out. Obviously, we've got to cut in wind speeds sort of below which, if the wind's not blowing enough, then we're not turning the turbine blades, so we're not getting any energy. And that's sort of region 1. Then we go through a ramp up to we reach our kind of rated power capacity for our wind turbine, which is then running at full operation capacity. But then if we're exceeding those wind speeds, we get a cut-off wind speed where we have to actually turn off the wind turbine. Otherwise we risk kind of causing damage, and then there might be conceptually another threshold where we actually get physical damage to the turbine itself from type of windstorm events. So what Sarah was doing was looking at each of these different regions and seeing how they might be affected by future climate change. To simplify things, obviously we were looking on quite a fine resolution grid, but we were wanting to summarize our results, and we summarized them in terms of sort of north, south, east and west of the UK. In order to define our boundaries, we base these on the shipping forecast regions of the area, with the basis that these would actually have some meteorological relevance as to how they've been kind of defined and separated, so that we could be, hopefully similar, that we were not arbitrarily picking lines as to how we would separate these different areas. So on to results in the kind of low region, wind region 1, which is where we're not sort of generating anything. We looked at the return period for various different thresholds of cut-in wind speed, so from sort of 4, 5 or 6 meters per second. And looked under kind of current sort of near future, sort of mid-century, 2021 to 2040 through, and then sort of end of century, sort of 2060 to 2080 conditions. And you can see that really the return time is decreasing as we go to kind of future climate conditions. So that means that we're seeing those low wind conditions more frequently in future climate, and really across all the different kind of wind cut-in speeds that we were looking at, but also perhaps they're slightly more rarer, that we'll get low wind conditions in the west and the north of the UK, which is perhaps not unsurprising to anybody who kind of knows anything about UK weather, than you do in the east and the south of the UK. In the maps, you probably can't see them very well because they come up quite smallly, but the green areas are actually where we have our installed wind farms or sort of possible kind of wind farm locations, and so we were looking to see how rare it is that we get these kind of events for various different wind speeds for those different wind farm locations. And you can see that in general it's much more frequent that you get these still conditions sort of nearer the coast of the UK, and as you go sort of further out, off to sea, then you've got kind of it's more rare that you get still conditions. But obviously, from an engineering point of view, for your wind turbines, it's probably easier to locate them close to shore than it is to have sort of more offshore variants. Then if we move on to think about this sort of production stage of the wind turbine curve and do the same sort of thing, we can see under future climate both the sort of monthly variation and seasonal variations are increasing with future climate. So the kind of variability in the wind speed is kind of increasing, which would disrupt your stability of your generation. But actually the capacity factor is decreasing, therefore, as a result, for each of the different regions with future climate change. The orange line on this is actually kind of where it becomes not really viable to do, sort of below this. So we're kind of well above that line in all of these scenarios. So it's not sort of saying that it's not worthwhile to have wind turbines there, but you know, we are saying that you know, particularly in regions like in the west of the UK, then we've got a higher kind of capacity factor that we're seeing. So that might be a good place to diversify our output, because quite a lot of the current kind of installed capacity is in the North Sea. The other aspect we want to look at is how things change in a seasonal sense. So we looked at the sort of left column is a wind power density for each of the different seasons for the kind of current climate, and then the difference for the two kind of future climate scenarios. And you can see that the wind power density is reduced during summer, and that you've actually got this is set to get kind of worse with future climate change, so you will get kind of even less generation there. And actually that this is kind of spreading a little bit further into autumn as well, in terms of where we're seeing this reduction in generation capacity. And so this is kind of important because we need to know yeah, how we're gonna kind of plug those gaps in generation, and you know, where we might want to think of installing things in the future. Moving on again through the wind turbine curve, we moving into sort of region 4. So this is where we were having to sort of shut off the wind turbine. This is where we're now looking at really gusts of kind of high speed wind that's causing kind of problems. You're more likely to see this again, so in terms of return time in the sort of northwest of the UK than in other areas. It sort of decreases to the south. But if we look into the near and far future, we can see that to a certain extent this gradient between the north and south of the UK is kind of smoothing a bit, so you're getting more windy conditions in the southern areas of the UK than you've seen sort of previously with future climate change. And so it's you know, going to perhaps mean that you know, perhaps the difference between siting in the north and south of the UK is less than it would have been previously for these types of events. just to finish things off, similarly, if we're looking at this, threshold for the magnitude that we'd expect for critical failure of the wind turbine, you see much the same kind of picture in terms of the kind of smoothing of the risk between the north and the south of the UK in terms of the likelihood of seeing gusts of these kind of magnitudes. So again, the strongest gusts are in the kind of northwest and kind of less intense near the coastal kind of regions. So what Sarah was doing in her thesis was then kind of comparing all of these things to then try and distill some information as to where are the best places that we might want to site these to be the optimal locations in the future. And so in some of these scenarios, the east coast in the North Sea of the UK is not looking so great. And our point is that maybe you actually want to diversify into some other locations to actually kind of give ourselves a bit more stability in our wind generation capacity. So now kind of moving on to a transmission example, and this is work that Eleanor McIndoe did as part of her MSc dissertation. So here she's back to looking at fires in Australia, in Victoria, and I guess 101 for I don't know what the background of the audience is, how much people kind of know or don't know. So I hope I'm not preaching to people who kind of already know all this stuff. But the sort of, I guess the point is that when you've got fires that are happening in the area of transmission, when you've got high temperatures, you're going to have greater sag of your transmission lines, and so you've got an increased risk that you're going to have flashover and maybe even stop causing fires because you're getting shortages between the lines, and you'll cause kind of damage to your transmission system. Adding on to that, once you're actually trying to pass power through your power line, it's going to heat up, which is going to add to the sag that you see. And so in operation, what we do during kind of high temperature events is maybe reduce the transfer of energy through the transmission system in order to prevent these risks. And they assign different kind of static or dynamic line ratings to the transmission lines in order to sort of say, well, we think this is the allowable bit that we could amount of current that we can pass through.
So when in her earlier charts where she had failure due to overload, that's because the operators have taken the lines out of commission, is it?
I'd have to check with back in her thesis, but I think it's probably due to overloaders in they've taken the line out of commission or derated it slightly. So what we've done here is then try and think about how we would define our event as a heatwave event as it would relate to the transmission system. And so here we've kind of looked at our ambient temperature on our transmission lines throughout sort of Victoria. And we've defined our event as sort of a mean 6-hourly ambient temperature over the transmission line area that is going to cause a problem. And then we looked at the severity thresholds, which we based on the kind of rated capacities, the dynamic and the static kind of line ratings as to what these temperature thresholds should be. And so she looked at the likelihood of, you have to forgive me because the returns I've got here is the other way round than all the other graphs that I've shown you up to this point. So here to the left, the event is getting kind of rarer, and here it's becoming kind of more common. So here she was looking at the mean ambient network temperature for the lines, and under kind of current climate, you'd expect to be meeting or exceeding this threshold kind of every 9 years or so. Whereas in a 2-degree kind of warmer climate, then you're seeing those kind of exceedances pretty much every year. So it's an increase of kind of 9.5 times. So this is kind of something that's pretty significant to think about in terms of how we're actually going to deal with this in the transmission system, and how we need to think about how we deal with these types of events. And this is where I come on now to some work that was done by Weijie Yang, who was a MSc student, but also went on to do her DPhil with us, and this is some of her DPhil work. And she was really looking at how to model and enhance the resilience under wildfire risks. So again, you've got this sort of not only fresh and new infrastructure, but aging infrastructure that might not be in the best repair. We've got kind of wildfire events, we've got outages that then occur as a result, which then leads to kind of both economic and kind of social losses. So we need to think about how we can build better resilience in the grid in order to withstand these sorts of events. So the approach that Weijie was taking was using fire weather index, so that's FWI, with a power system model. So here I've got each of the different meteorological variables that go into calculating fire weather index. And then on the top right, the fire weather index itself, but also there are risk levels that are associated with the fire weather index. So you can categorize it just on this sort of numeric scale that's going on, but you can classify it into various different risk bands, which is what we did. Taking various different threshold values from kind of low through to extreme. So you can see that there are, during this particular illustrative day or time, there's a large amount of the transmission network that's in a kind of low risk area, but there are some that are in quite high risk environments. So what we did was then try and look at the line loading of each of the transmission lines. So we can kind of consider, if we take the thresholds that were set by the fire weather index as to event sort of severity, as to see what that would do for how many lines we'd have to kind of disconnect if we kind of based our reference on that kind of indicator. So when we've got the kind of like highest threshold in the most sort of extreme cases, if we're happy to accept that risk, then we don't have to disconnect any of the lines through to, if we've only got appetite for a high risk, then we're starting to disconnect kind of 36 of the lines that we've got there. So, although we sort of like, it's a bit of an optimization problem, because although we want not to have too high a risk that we're going to either cause fires or have disruption or failure of our equipment due to the fires. If we start kind of looking at the costs and the carbon emissions associated with the running of this, then they increase as we kind of like go to lower thresholds as we're having to disconnect more things. So what Ouija was looking at was adding in some additional wind generation kind of close to the points of failure at the sort of vulnerable nodes to recover the shed load. Now, when you do this, the kind of we get less carbon emissions, but the operational cost goes up quite high in terms of the costs here from the total system. But if we start to think about the value of lost load, which is all the sort of economic and social costs associated with having to switch off or derate some of these transmission lines and affecting disconnected customers, then we can see that the overall the sort of overall system cost is a lot better when we kind of add in this additional generation at these places. So we can use this sort of framework to then calculate where the sort of break-even point for renewable wind sort of distribution might be, and where it's actually sensible to kind of add in this enhanced generation into the system to kind of combat things in these particular cases. Now marching my way through my diagram into the distribution network now, and this was an example of some work from a fourth year undergraduate student project, which was looking at substation flooding in Norfolk. So what we did in this was to look at various different catchment areas, river catchment areas within Norfolk, but think about where the individual kind of primary and secondary substations are. So that's what this kind of map is showing you, and also highlighting where the sort of three main demand centres are in Norfolk as the kind of major different towns. Because we were slightly constrained in the fourth year project, we were taking some pragmatic decisions rather than doing kind of full-on hydrological modelling in each basin, but we were basing our sort of trying to define some rainfall thresholds which were associated with flooding or past flooding events that had happened in the different areas. So here we've kind of illustrating where historical events were, and the definition that we decided on was really the sort of top 5% of rainfall, 5-day accumulated rainfall days over a climatological period as being the reason of where we would set our threshold to be. So Dermot was considering kind of the changes in risk because of the precipitation that was occurring, but also kind of acknowledging, got caught up that obviously there are other additional risk factors. And if you kind of talk to UK power networks, they have different severity indicators that they're looking at in terms of risk. And that might be things like how many transformers they've got on site, how many customers they're serving, whether the particular substation that you're looking at is located indoors or outdoors, might be kind of influential factors. The other thing as well is difficulty of maintenance. So where are these things located? How close are they to the nearest road network in order to actually get to them in order to help fix them when things go wrong. Or when there's a sort of a flood event in place. And then also we sort of use the Environment Agency for flood risk maps in order to sort of like guide the specific locations that we know were susceptible to flooding. So Dermot combined all of these factors to come up with a sort of a normalized risk factor for each of the different kind of primary and secondary substations. You can see that really with the primary substations, a lot of them are in sensible kind of places, as you might expect. So their risk of being kind of flooded was kind of like fairly low. Whereas we've got a bit of a broader spread with some of the secondary substations that are there. Yes, what we were doing was then taking this risk, looking at the projected kind of impact of climate change. So again, unfortunately, was increasing the likelihood that we were seeing these type of events, not as significantly as things like the heat waves in Victoria, but nevertheless, increasing the likelihood in particular locations. So Dermot was then thinking, well, how can I make good use of this information and turn it into something a bit more practical that we can use to inform decisions? And so he was then saying, okay, if we take the risk under future climate and we think about the sort of top 95th percentile for the substations that are actually changing risk, what is the largest change in risk that we're seeing? Then we get a sort of subset of those different primary and secondary substations, and there's lots of spatial detail in zoomed in areas. But we also know that not all of these are in the same kind of state of repair, and that actually they have maintenance cycles where they're due to be upgraded under certain kind of cycles. So Dermot used this information to think, okay, if we're going to be upgrading this sort of in the near future anyway, then we can just upgrade or reinforce our substations when we are in the near future when we're doing our scheduled upgrade. But really it's sort of like the case of things where it's got a long time before we'll do our next scheduled upgrade, but our risk has massively increased. Then we can use that information to prioritize, come up with a priority of which kind of substations we might be seeing first. So he came up with this sort of substation protection priority kind of level as to which ones are the ones that we might want to go to first in order to do out of maintenance cycle reinforcements. So it's ways that we can use this kind of attribution information to inform our decisions or inform where we should be prioritizing our action to help make the system more resilient as a whole. Then finally, onto the demand side of my walkthrough diagram. And this is really work that's again from a number of students. Again, this is work from Albury, which was another fourth year undergraduate project. And we're looking at the heat dome in the Pacific Northwest. So I don't know whether any of you remember, probably in lockdown, just after lockdowns, was this really large heat wave event that was associated with a kind of heat dome in the Pacific Northwest. And the temperatures got really, really high in the area. Now, if we actually then look at where the deaths are as well, which is not the cheerfulest thing to look at, but it's sort of telling us something about the impacts. We can see that these are correlating kind of a bit squint with the kind of high peak temperature areas that we're seeing. And actually I've put a red box around this because these particular areas were served by the same electric company. So we were able to kind of look and dig in a little more into their demand data. So I guess here's a sort of temperature demand curve for that particular region over, a reasonable number of years. So, as you might expect, as the weather gets colder, we turn on our heating and our demand goes up. But then again, as the temperatures increase, we also get kind of more desire for air conditioning and our demand also goes up. Highlighted are the heat wave days, which are not unsurprisingly on the high side of this kind of demand curve. But the thing that's important is that the total demand is actually higher on the high heat wave days than it is during the really cold days when we've got our heating systems on as well to warm us up. Yeah.
Point saying a heat wave up to 15 degrees.
I'm not sure about this point. I think it must be because we're looking in terms of defining the heat wave as an anomaly from the climatology, and maybe this was a heat wave, but in a kind of cold winter condition. So it's sort of a slightly strange looking point that's on there, but yeah.
And then you say heat wave and death, which kind of death?
So I just think it's increased mortality. I don't think that we actually looked at making seeing whether it was cardiovascular related or different kind of types of outcomes. I think it was just in terms of excess mortality. Yeah.
Is heat wave just temperatures?
So that's a very good question, or a very good point. In the way that we've defined things here, we defined it purely in terms of temperature. But if I was doing and have done when you're looking in terms of human health or human kind of comfort, then you're wanting to include things like the humidity as well, and also the nighttime temperatures are particularly, I think, important as well as to how much respite you're getting overnight from those sort of high temperatures that you're seeing during the day, and that can really affect people's system and how well they can cope with these sort of high temperature events. Yeah, so we've done some stuff before where we're looking at the wet bulb growth temperature and also kind of other indices of thermal comfort. However, as we were from what we were showing here, we were just looking at the temperature relationship for this. So that was what Aubrey had done, but we kind of for another MSc dissertation student, Natalie, from last year, we took this idea and actually applied it to Brazil a little bit more rigorously to look at how future demand might change, or how the projections are. So in terms of Brazil, where we were looking at was mainly on three different kind of areas or regions: the northeast, the southeast, and the south of Brazil. I think it's worthwhile kind of saying that this is where the largest kind of population density is, so this is kind of a sensible place to look at when kind of picking different areas. But we also have a difference in terms of wealth between the different parts of the north and the south of Brazil and this area. The top plot is actually showing a projection of population growth in Brazil, which is worth bearing in mind, so it's going to sort of projected to peak just after 2040, and then they'll see a decline in their population. So what Natalie was doing was then looking at various different metrics around heat waves. So it was looking at the frequency of heat waves. This again is a sort of a now mid-century, end of century target or projection for each of the different areas that she was looking at. So we can see that they're increasing in frequency quite a lot in the southeast, which is not great because that's where your big Rio, Sao Paulo, big centres are. But also the duration of the heat waves were increasing in each of the areas. But you know, there's not much difference in the intensity of the heat waves that we're seeing in the way that we're measuring. In the bottom, she used those kind of temperature demand curves and modeled them sort of specifically for each of the individual areas to then get a sort of total annual demand and kind of combine that with the population data. So that's where while you're seeing these sort of tail off as the population declines in future years, but these are different SSP scenarios, so different levels of kind of climate change that is expected to happen in the future. So you can see that in terms of the demand, it's being hugely driven by population more than necessarily what the climate is doing, although the climate is kind of making things worse, and it is worse there. But then equally, when we reach this sort of peak in sort of 2040, 2050, that's going to cause kind of maybe the stress, the kind of maximum stress point, I think, for them to deal with different kind of demand ideas. Now this is my last slide, apart from my conclusion to repeat here. So this is then also some other work that we're doing with not students this time. This is us looking at large ensembles, looking at cooling degree days. So as a sort of pseudo metric of demand and how they might change between a 1.5 degree and a 2 degree warmer world. So if we're looking at the sort of absolute change, then as you're expecting, the amount of cooling degree days is kind of it's increasing massively in the sort of tropical regions, which is then a big challenge. If we're then actually thinking in terms of the relative change, then we see a different pattern emerging where, you know, in the sort of more northern regions where you're not so used to having air conditioning kind of installed, you have got the sort of most increase in cooling degree days relatively. So that means that you've probably got a large adaptation challenge in order to deal with this increased demand that will be coming. So to conclude, and I'm just going to keep it brief in 3 kind of chunks. So I think what I was trying to convey is that climate change is impacting all aspects of the energy system in different ways through extreme weather. We need future development in order to actually enhance our resilience to these types of extremes in the future. But we can use techniques such as the extreme event attribution to help kind of guide or target our efforts into where we should concentrate our efforts to improve resilience first. I'll leave it there.
Okay.